Okay, doke. Then the last thing that we'll discuss in Chapter 6 is how we optimize multivariable functions. Now that we know how to find derivatives, this is now available to us. This is something that's now possible. Let's recall what that optimization process looked like in Chapter 4. If you had your function, in order to find the local min and local max, the first thing we had to do was figure out critical points, which was when the derivative was equal to 0. Now this is a little bit more complicated for partial derivatives because which derivative do I use? If I've got two independent variables, then I have two partial derivatives. I have f sub x and I have f sub y. Which one do I want equal to 0? Well, it turns out with multivariable functions, you want both of them to equal 0. You want all of your partial derivatives to equal 0. So we consider a, b, if I'm working with two independent variables, we consider it a critical value or a critical point if f sub x is equal to 0 and f sub y is equal to 0. So both have to be equal to 0 for it to be a critical point. So let's look at my two partial derivatives. Let's take the derivative first in terms of x. I get 3x squared plus y cubed doesn't have any x term in it, and so that just goes to 0. Minus, I'm going to treat the x as my function and 6y as my constant. What's my derivative of x? My derivative of x is just 1. So I'm left with this, 3x squared minus 6y. My partial in terms of y is going to be pretty similar. You get 3y squared minus 6x. If you're still a little confused about those partial derivatives, either rewatch my 6.2 video or shoot me an email and we can go over it a little bit more. So like I said, we want both of these to equal to 0. So let's start with my partial in terms of x. Let's just take these one at a time and see what happens. So you'll notice I now have an equation that's in terms of two variables. That means I'm not going to be able to solve for a specific value yet. The best I can do is solve for y. Okay, I'll move it over to the other side of the equal sign. I'll add 6y on both sides and divide by 6, and I get y is equal to 1/2 x squared. So that's the best I can do. But what does this actually tell me? This right here, this equation tells me that as long as this is true, then my partial in terms of x will equal 0. As long as that's true, our partial of x is going to equal 0. So now, let's go back and let's go to my partial in terms of y. Now, like we said, we want both of these to equal 0. So what I will do is I'm going to rewrite this by substituting 1/2 x squared in for y. Why do I do that? Because as long as y is equal to 1/2 x squared, my partial in terms of x will equal 0. This guarantees that f sub x will equal 0. By making that substitution, I'm guaranteeing that f sub x will equal 0. So now, I just need to worry about setting this equal to 0, because I want my partial in terms of y to also equal 0. And now I can solve. And what's nice about this is that, so I'm going to square 1/2 x squared. I get 1/4 x to the 4th. What's nice about this is now it's all in terms of x. I get 3/4 x to the 4th minus 6x. I can factor out an x, and in fact, I'll go ahead and factor out the 3/4 as well. I'm going to factor out 3/4 x, and I'm left with x cubed minus 8. Okay, this gives me two possible critical points. If I focus on this term, that gives me the critical point of x equals 0. And then if I focus on this term, I can set that equal to 0 and solve for x, and I get positive 2. So two possible critical points. Now, but you'll notice I only have the x value for these critical points. How do I find their corresponding y values? Because recall, since I'm working with a multivariable function, my critical point needs to be both the x and the y value. The x and the y value. So I need my corresponding y values for both of these. How do I find those? I can use this equation. Remember, that equation is what guaranteed that f sub x was going to equal 0. So I can go and use that equation to figure out my corresponding y values for each of these. So for 0, if I plug in 0, I get 1/2 times 0 squared. That's just equal to 0. So my corresponding y value is 0, and that's one critical point. Well, I can also plug 2 in, see what I get. 2 squared is 4. 4 divided by 2 is 2, and so my corresponding value for x equals 2 is y equals 2. And there's my other critical point. So I have 2 possible critical points. But just like we talked about in chapter 4, just because something's a critical point doesn't mean that it's a minimum or maximum. We also don't know whether it is a minimum or a maximum. So how do we figure that out? Well, working with multiple variables, the first derivative test gets pretty complicated. So instead, we're going to look at a version of the second derivative test. So let's talk about this second derivative test for multivariable functions. And with each of these, it gets even more complex as we move on to like even more variables. So we're going to focus on 3-dimensional functions. So this is the second derivative test for 3-dimensional functions. Why is it 3-dimensional? It's because you've got 2 dimensions in just your independent variables, right? X and Y represent 2 dimensions, and your output is your third dimension. So what we're going to do here is we're gonna find what's called a determinant. So we're going to use D for determinant, and what we're going to do is we're going to do the double derivative of x evaluated at my critical point times the double derivative of y evaluated at my critical point minus the mixed derivative f sub xy evaluated at my critical point squared. Now remember, that mixed derivative, it doesn't matter what order you do it in. If you did y first and then x, you'll get the same value. So that's why, so don't stress about, oh, it has to be x then y. No, it doesn't actually matter. Okay? And so let me remind you where AB is a critical point. So I'm going to calculate this determinant, and then there's 3 different options that could happen. 1, if D is greater than 0 and your double derivative in terms of x is greater than 0, so positive. So if your D ends up positive and your double derivative in terms of f is positive, well, remind me, what did a double derivative, what did my second derivative being positive tell me? That means I'm concave up. That means this is a minimum. This is a minimum. So hopefully you can kind of see how this connects to my second derivative test for my normal 2-dimensional functions. Okay, well, similarly, if D is greater than 0, so if my determinant is still positive, but my double derivative is negative, then you're working with a maxima. And I'm using the double derivative of the x. It turns out if you use the double derivative of y, the same should be true. If your determinant is positive, that means that your double derivatives for x and y are both the same sign. Otherwise, you'd be getting a negative for you'd be getting a negative value for this piece, and then this piece is always positive because you're squaring it. And so you're guaranteed to get a negative value, which is what we'll actually talk about in this third option. So let's say that happens and your D value is negative, your determinant is negative. Well, what does that mean? That means your double derivative in terms of x and your double derivative in terms of y were different signs. And so that means that it's not necessarily, it's not a minimum or a maximum. We call this specific situation a saddle point. Then there is a saddle point at AB. What is a saddle point? Well, here, let me do my best to draw a 3-dimensional function here three-dimensional functions, we do something like this, where this is my x, this is my y, and this is my output. Sometimes you notate it at z, but since that represents the output of my function, I'm going to notate it using function notation. Well, let's say the saddle point is a situation where we found a critical point where let's say along my y-axis, I have a maximum. I have a local maximum along my y-axis. But then along my x-axis, I have a local minimum. And so what's happening is along this x-axis, I'm sloping up, but then along this one, I'm sloping down. And what happens is it creates this cool shape that looks like, it's called a saddle point for a reason. It looks like a saddle. It looks like something you can sit in. And it doesn't represent a minimum or a maximum. There is one more situation that might happen. What if d is actually equal to 0? Well, this is a special situation where this is inconclusive. But that's my second derivative test for three-dimensional functions. So let me put a big old box around this. So now let's revisit the critical points that I found in this problem. Okay. Well, in order for me to use this second derivative test, I need to have my second partial derivatives. I need f sub double x and f sub double y. So let's go ahead and calculate those real quick. F sub double x is just your partial in terms of x of your partial in terms of x. So now I'm going to take the derivative of that in terms of x, and I get 6x, and then minus 6y is only in terms of y, so that's going to go to 0. So I just get 6x. Partial in terms of y, again, right? My double derivative in terms of y, I'm going to take the partial in terms of y of this, and I get something very similar. I just get 6y. What about my partial of xy? If I take the partial in terms of x and then take the partial in terms of y, well, if I take the partial in terms of y of this, that 3x squared term just goes to 0 because there's no y in it, and I'm just left with negative 6. If I take the derivative of negative 6y in terms of y, I just get negative 6. Notice, if you switch the order and took the derivative of this in terms of x, you would just get negative 6. So we can see that it turns out nicely the way that it's supposed to with this problem. Okay, so now let's try this determinant out. I'm going to do the partial of x with, let's start with 0, 0, with my critical point plugged in, times the double derivative in terms of y with 0, 0 plugged in, minus the partial in terms of xy, which is just negative 6. This one doesn't depend on your point at all, squared. And what do I get? What happens when I plug 0 into my double derivative of x? I just get 0, right? 6 times 0 is just 0. Notice there's nowhere for me to plug the y value in because it doesn't depend on y at all. So I get 0. Same thing with the partial in terms of y. When I plug 0 in for y, I just get 0. Minus negative 6 squared is 36. I'm left with negative 36. So what do we notice about my determinant? My determinant is less than 0 at the point 0, 0. So what does that tell me about 0, 0? It's a saddle point. So 0, 0 is a saddle point. Okay, well, let's try the other one. So now let's find the determinant. Let me zoom in a little bit so it's a little thicker. Let's find the determinant at the point 2, 2. Okay, minus, of course, the mixed derivative, f of xy at 2, 2. Well, for both of these, for the double derivative of x and the double derivative of y, I'm just plugging in 2 for x and 2 for y. So what do I get? I get 12 for this partial derivative and 12 for this double partial derivative. Minus, and then f sub xy of 2, 2. Remember, that one didn't depend on x or y at all. It was just constant at negative 6. So I still have negative 6 squared for that piece. Well, this leaves me with 144 minus 36, which is positive. So in this case, I get a positive value. So my determinant is greater than 0. So, but remember, if the determinant's greater than 0, there's actually more criteria that I need to test. So, right, that falls under these two categories. It's either 1 or 2. And it depends on what's true about my double derivative in terms of either x or y. Both of these were positive. What does that mean? That means I'm concave up and I'm working with a minimum. So I have a local minimum at 2, 2. Let's try an applied problem from the homework. So this is number 6. And I've got it pulled up over here on the left. A trash company is designing an open-top rectangular container, so 3-dimensional, that will have a volume of 320 feet. So I know volume is equal to 320. The cost of making the bottom of the container, so the bottom side, is $5 per square foot. And the cost of the sides is $4 per square foot, I guess because they don't have to make them as strong, the sides. Find the dimensions of the container that will minimize total cost. What does this sound like? This sounds like an optimization problem. But optimization problems, all they are is finding your minimums and maximums. What are we going to use? We're going to use derivatives. But this will be slightly different because it's a multivariable. This is going to be a multivariable function that we're going to be working with. Well, let's take a look at volume. I know my volume is 320. There's my constraint. And how could I write volume? Well, volume is just length times width times height. Okay, interesting. So that's what we have so far. Let's see, we're trying to minimize cost. So let's see if we can come up with a cost equation. So C is going to be my cost equation. And first of all, it costs $5 per square foot for the bottom of the container. So it's $5 times the area of the bottom because it's per square foot. Well, how do I calculate area of the bottom side? I can just do length times width. So that takes care of the bottom of my bottom of my container. If we want, sorry, I should have done this earlier, draw a picture to help you out. So here's my length, my width, and my height. So now I need to get the sides. Well, it's $4. So if I just look at this side, it's $4 per square foot for that side. So that's going to give me 4 times width times height. But how many of those sides are there? There's actually this side on the other side is going to be the exact same size because this is a rectangular container. Both of those sides will have equal areas, so I can just take that and multiply it by 2. Now, if I look at these front sides, what's the area of this front side? The area of this front side is length times height. So it's $4 for that area. $4 per square foot for that area. How many of those areas do I have? Well, I have 2 because I also have the back side. Similarly, I'm also going to multiply that by 2. What does that leave me with? That leaves me with 5 times L times W plus 8 times width times height plus 8 times length times height. So at this point, I could go ahead and start taking partial derivatives. I could take the partial derivative in terms of length, partial derivative in terms of width, and partial derivative in terms of height, and have 3 different partial derivatives. And if you remember, when I work with these partial derivatives, if I'm looking for a critical value, I'm looking for where all of my partial derivatives are equal to 0. But if I do that right now, I'm actually going to end up with lots of possible critical points. What have I not used yet? I haven't actually used my constraint. I do have a constraint here that the volume has to equal 320. Well, what does that help me do? Well, that helps me do is solve for one of these variables. If I solve for h, I get 320 divided by length times width. All I did was just divide both sides by length and width. Now I can substitute that in to my cost equation, right? This looks similar to what we did with my applied optimization problems. So what does that leave me with? When I sub that in, I get 5 length times width plus 8 times width times, right? I'm subbing this in 320 over length times width. And then I'll do that over in this last term because I have 8 times length times height. But once again, I'm going to sub in 320 over length times width. And let's see how this simplifies. when this simplifies, I get 5 length width plus 2,560. That's 8 times 320. But notice that I have a width in the numerator and a width in the denominator, and those are going to cancel. So the only variable I'm left with in this term is an L in the denominator. This second term is also going to, or this third term is also going to simplify in a similar way, except it's going to be left with a width in the denominator because your lengths are going to cancel. Now I'm down to 2 variables. I've already used my constraint, so there's nothing else I can do to get this down to only 1 variable. So at this point, we can go ahead and start taking partial derivatives. All right, I still have 2 independent variables, which means this is going to be a partial. I'm going to be finding partial derivatives, which makes sense. We're in chapter 6. That's what chapter 6 is all about. If I take the partial in terms of my length, well, this first term, I treat the 5 and the w as a constant. And what do I take? When do I get when I take the derivative of L? I just get 1. So I'm left with 5w. This next term, I could rewrite as 2,560 times L to the negative first power. And that gives me the following derivative. I get negative 2,560 over L squared. And then my third term doesn't have an L in it at all, so that term just goes to 0, which means I don't even have to write that. Your partial derivative in terms of width is going to be very similar because this function is kind of symmetric. You're going to get 5L minus 2,560 over W squared. So where do I go from here? I've got my partial derivatives, but both partial derivatives still are in terms of 2 different variables. Well, this is where I take them one at a time. If I look at this first partial equation, I can solve for W. Let's solve for W. Solve for W by doing what? Remember, we want these partials to equal 0, so I'm going to set this equal to 0 and then solve for W. Okay, if I do that, I get, let's do this in blue, I get 5w equals 2,560 over L squared, divide by 5, and you're left with w equals 512 over L squared. So that's what my width is equal to. And like I said earlier, what this means is as long as this is true, as long as your width is equal to 512 divided by your length squared, then the partial in terms of your length will be equal to 0. So I'll use that then by plugging this into my other partial derivative. What does that give me? That gives me 5 times L minus, I get 2,560 divided by 512. That actually just leaves me with, you get 2,560 over, that W is squared, so I'm actually going to square everything. I have 512 over my length squared, all squared. Okay, what does this leave me with? This leaves me with 5 times my length minus, well, because I have a fraction in the denominator, if you recall, I can flip and multiply after I distribute this power. Because it's division, you can go and distribute that power to both your top term and your bottom term. And then I can flip and multiply. What am I left with? I'm left with 2,560 L to the 4th over 512 squared. 512 squared is a pretty big number. It's like 200,000 something, but it does just simplify to this. Let me go and show you what it simplifies to. It simplifies to minus 5 over 512. So that's what I'm left with. That is my partial in terms of W. That's now completely in terms of my length variable, which is awesome. And we've already taken into account, this is already done. We've already taken this into account, so we're good to go. Now that it's all in terms of one variable, I can set it equal to 0 and solve and see what I get. Well, I'm going to want to factor this. When I factor this, I can factor out a 5L. Both terms have an L. Both terms have a 5 in the numerator. And I'm left with 1 minus your length cubed over 512. What does this mean? So because I was able to factor it, that means I have 2 possible critical points. One for my first factor and one for my second factor. Well, what critical point is that first factor going to give me? if I set 5L equal to 0, that tells me that my length is equal to 0. Is that a valid critical point? No, I can't use that one. I can't have a rectangular container whose length is 0. Of course, that's going to minimize my cost. So that's not going to work. Can't use this one. So it's all based off of this second one. When I set that equal to 0, what do I get? I get, I can add length cubed over 512 to the other side, then multiply by 512, and I end up with 512 equals length cubed. Take the cube root, and you get 8. That is a possible critical point. Okay, so there we go. And notice I only have one critical point, so I don't have to test whether this is going to give me a minimum or maximum. I can go ahead and assume this is going to give me a minimum cost. But there's one of my dimensions. Now let's find my other dimensions. Okay, so my length is equal to 8. How do I figure out my other ones? Well, here's an equation I can use. What is that going to help me solve for? That's going to help me solve for the width. I know my width was equal to 512 over length squared, so I get width equals 512 over 8 squared. Well, that's 512 over 64, which, guess what, is equal to 8. So, sure enough, my optimal area, or in order to optimize the cost, I need my base to be a square. Last, I need to solve for height. How do I do that? Well, I can now use this formula. Remember, this one was based off of my constraint. This will make sure that my volume ends up equaling what I want it to. So that is 320 divided by length times width. Well, that's just 8 times 8, so 320 over 64, and I get 5. There's my dimensions. My length is 8, my width is 8, and my height is 5. Let's check to see if this is actually right. 8 by 8 by 5. Notice I'm putting the height last because that's how it's listed right here. Length times width times height. Okay, let's try it. Oh, good. I was pretty confident since my answers were whole numbers. If you're not getting whole numbers, something's wrong. But, okay. Good luck on the homework. Let me know if you have questions.